This is the 18th video in a series devoted to differential equations. Today we're going to look at something called the Laplace transform. So let's jump right into the definition. So let's say we've got a real valued function f whose domain includes the non-negative real numbers, so the interval from 0 to infinity including 0. Then the Laplace transform of f is this function f of s, which will use this notation of this script L, applied to f of t, and that is equal to the integral from 0 to infinity of e to the minus st f of t dt. So let's notice this integral is with respect to t, so that means that definite integral with respect to t will remove the dependence on t and leave us with a dependence on s. Okay. Then we've got this duality between a Laplace transform and an inverse Laplace transform, which we might as well define right here. So in this setup that we have up here, we would say that little f of t is the inverse Laplace transform of capital F of s. And we would write it like this. So we've got little f of t, inverse Laplace transform of capital F of s. And there's no real good formula for finding the inverse Laplace transform. You kind of have to know where you are coming from. Just like when you're doing derivatives and antiderivatives, there are really nice derivative rules, but finding antiderivatives is a little bit more of a creative endeavor. Same thing here. Okay, so let's maybe look at the question of why we would want to look at or study the Laplace transform in the first place before we look at some examples. So the Laplace transform has this nice property that it will take a differential equation and change it into an algebraic equation. Now, this is not always the case, but for a huge family of differential equations, this is like how it goes. And this is essentially what we'll use the Laplace transform for. Okay, so back to our chart. Let's say we've got a differential equation that we don't know how to solve. Well, we could apply the Laplace transform to this differential equation, and that'll leave us with an algebraic equation. And perhaps we know how to solve that algebraic equation. That'll give us the solution to this algebraic equation. Well, we could take that solution to our algebraic equation, apply the inverse Laplace transform, and what we'll end up with is a solution to our original differential equation. So by taking this path, which is maybe the long way around, versus this quick path, we're able to solve differential equations that would have been too hard to solve directly. Okay, so now that we've got an idea of why we might want to study the Laplace transform, and we've got a definition of the Laplace transform, let's start calculating this transform for some functions. So let's look at our first examples of calculating the Laplace transform. We'll start with the constant function 1. Okay, so we'll say that f of t equals 1 in this case, and we want to calculate this capital F of s, which is, like I said, the Laplace transform of f of t in this case. So here we'll have the integral from 0 up to infinity of e to the minus st dt, nominally times the number 1, but that doesn't really change anything. So here we can simply take the antiderivative. We're taking the antiderivative with respect to t. That will give us minus 1 over s times e to the minus st. Then we need to evaluate that from 0 up to infinity. Keeping in mind that when we say evaluate it at infinity, what we really mean is take the limit as t tends towards infinity. So let's notice as long as s is positive, the limit as t tends towards infinity will give us 0 up there because of exponential decay. Then if we plug in 0, we'll just get the number 1, but that's the lower bound, so in the end, that'll give us 1 over s. And this, like I said, is when s is bigger than 0. So this is interesting already. Let's notice that the Laplace transform of our constant function was a non-constant function. The Laplace transform of the constant function 1 turned out to be this reciprocal function 1 over s. Okay, so now let's look at maybe the ultimate generalization of this type of setup. If we think about the number 1 as being t to the 0 power, And we'll find the Laplace transform of f of t equals t to the n, where n is some non-negative integer. Okay, so let's get to it. So we need to calculate f of s here, which is going to be the Laplace transform of t to the n. I'll write it like that instead of the Laplace transform of f of t in this case, given that we have f of t is t to the n. Now here, this will give us the integral from 0 up to infinity, and then we'll have t to the n e to the minus st dt. But check it out. What we have here is a polynomial, t to the n, times an exponential. But anytime you have a polynomial times an exponential, that really tells you that you should probably use integration by parts. But since n is arbitrary here, you have two choices. You can kind of see what the pattern is doing and maybe make a guess of what the solution would be, or you could do something more careful with a proof by induction. We'll just kind of play it fast and loose, given that in a differential equations class, you're generally not super careful about this stuff. So let's do integration by parts, and we'll do it with the DI method, or the tabular method. Okay, so if you recall, we'll make the left-hand column the column that we take derivatives down, and that will start with our polynomial. In this case, it's t to the n. We'll take our I column, the column that we take antiderivatives. That'll be e to the minus st. Okay, so let's notice after our first derivative, we'll have n times t to the n minus 1. The second derivative will give us n times n minus 1 times t to the n minus 2, all the way down. Notice our nth derivative will give us n factorial, and then the next derivative will give us 0, because n factorial is a constant. Okay, so just to reiterate, this is the first derivative, the second derivative, all the way down to the nth derivative. That means here we need the first antiderivative, the second antiderivative, all the way down to really the n plus first antiderivative, given the fact that we're going to match on the diagonal. Okay, so the first antiderivative will be minus 1 over s e to the minus st. The second will be positive 1 over s squared e to the minus st, because the two minus signs will cancel. And then all the way down here at the very end, we'll have minus 1 to the n plus 1 over s to the n plus 1, and then e to the minus st. So we'll have something like that. And while we're at it, let's put the 1 right above it, which would be minus 1 to the n over s to the n e to the minus st. And the 1 right above this n factorial will actually be n factorial times t. You don't get less than n factorial until the 1 above that. Okay, so now let's recall that we need to match on the diagonals. That's like a result of this playing the role of repeated integration by parts. And then change the sign. So this is attached to a plus sign. This next one is attached to a minus sign, a plus sign. All the way down here, this will be a minus 1 to the n minus 1, and this will be a minus 1 to the n. Okay, and now let's keep in mind we have to evaluate at 0 and infinity. Well, we'll assume that s is bigger than 0, so that means when we evaluate at infinity, we'll always get 0 because the exponential term will win, if you will. Then if we evaluate this at 0, we'll get 0 almost all of the time. We'll get it for this t to the n times 1 over s e to the minus st. We'll get it for the t to the n minus 1 term, all the way down to this n factorial times t term. So just to reiterate, all of these will cancel out. So up to there, and this is the only one that we're left with. And then we'll evaluate that at 0 and infinity. Okay, so let's write this down. So that's attached to a minus 1 to the n. So we'll have minus 1 to the n. And then we've got a minus 1 to the n plus 1 from this built in. And then we'll have an n factorial over s to the n plus 1 and an e to the minus st evaluated from 0 to infinity. This is the only bit that does not give us 0. Okay, next up, let's notice that these two terms cancel to minus 1. So that's pretty clear because we have 2n plus 1 in the exponent. And then evaluating this at infinity will give us 0. Because we're assuming that s is bigger than 0, we get exponential decay. Evaluating this at 0 will give us 1 for the exponential part, but it's in the lower bound. That coupled with this -1 will cancel out and give us a +1, and we're left with n factorial over s to the n plus 1 in the end. So maybe reading it from here to here, we've got a nice closed formula for the Laplace transform of the nth power of t. So just to reiterate, the Laplace transform of t to the n is n factorial over s to the n plus 1. Okay, so let's get rid of this, start a chart over here of Laplace transforms, and do some more examples. So we've started to build our chart of Laplace transforms and inverse Laplace transforms over here. So we've discovered that the Laplace transform of t to the n, where n is a non-negative integer, is equal to n factorial over s to the n plus 1. And this is true when s is bigger than 0. Okay, so now let's find the Laplace transform for some other families of functions. Starting next with the exponential function e to the at. So this will give us the integral from 0 to infinity. We'll have e to the minus st times e to the at. But then let's notice that this is the integral from 0 to infinity. We can put those things together and get e minus s minus a times t. But now we can take the antiderivative of this just like before. That'll give us -1 over s minus a, and then e to the minus s minus a times t evaluated from 0 to infinity. And then if s is bigger than a, then we have a negative exponent, which means when we evaluate it at infinity, it zeroes out. And then regardless of what happens, if we evaluate it at 0, it'll always give us the number 1. That's in our lower bound, so that means in the end, we have 1 over s minus a. Like I said, this happens when s is bigger than a. Okay, so we'll add that to our chart over here, but before we do that, let's do a theorem that's related to this example. So the theorem we'll look at is sometimes called the first shifting theorem, or maybe the first shifting lemma, and it relates to this Laplace transform of the exponential function when that exponential function is being multiplied into maybe an arbitrary function. Okay, let's see what we've got. So if f of s equals the Laplace transform of lowercase f of t, and that holds for s bigger than s naught, then the Laplace transform of e to the at times f of t is equal to f of s minus a. So in other words, it's the original Laplace transform just shifted over a units. And this holds for s bigger than s naught plus a. Okay, so let's see how this goes. It's actually a fairly straightforward calculation. So the Laplace transform of e to the at times f of t, so that'll be equal to the integral from 0 to infinity of e to the minus st, e to the at times f of t by the definition of the Laplace transform. Then next up, we'll take these two exponential functions and put them together much like we did over here. And that'll leave us with the integral from 0 to infinity of e to the minus s minus a times t times f of t dt. But let's look at this. This is exactly the Laplace transform where we've replaced s with s minus a. So that brings us to our result. This is the Laplace transform of the original function where we replace s with s minus a. Okay, so that's good to keep in mind. Okay, so let's get this Laplace transform of our exponential function on the board, and then we'll do some examples. So I put that previous result as the second line of our chart. And that is that if we take the Laplace transform of e to the at times g of t, we get capital G evaluated at s minus a, where we've got this standard relationship between the lowercase functions and the uppercase functions. So in particular, if g is just the constant function 1, then capital G will be the constant or the function 1 over s, but then when we multiply by e to the at, its Laplace transform will be 1 over s minus a. So this captures like the basic one as well. Okay, so let's look at some examples. We've got two Laplace transforms and two inverse Laplace transforms. So here we've got 3 times t to the 4 times e to the minus 2t. So we have not proven this, but the Laplace transform is a linear transformation on the space of like appropriately defined functions. That being said, that's really easy to check just given that taking an integral is a linear transformation. Okay, so notice that this essentially acts like t to the 4th, but then we've shifted it by a plus 2. We shift it by the opposite of the sign here. Okay, so let's recall that we should get something like this. We should get like 3 times 4 factorial. From this 4 here, notice that the n here becomes an n factorial. And then down in the denominator, we'll have something to the 5th power. That's because this n here becomes an n plus 1. But what do we have in the denominator? Well, we need to apply this shifting, so we'll have s plus 2 to the 5th power. It's shifted by negative 2, but notice that it's shifted by negative 2, so that gives us a plus 2. So we could simplify this if we wanted to. 3 times 24 is 72, and then we have over s plus 2 to the 5th power. There, we calculated that Laplace transform. Now let's calculate this next one. So like I said, the Laplace transform is a linear transformation. We won't worry about proving that. Here we have t e to the 5t. So by our rule, t will turn into 1 factorial over s squared, but then it's been shifted by 5 units. So we'll get 1 factorial, which is 1, over s minus 5 squared. Great. Again, because of the shifting. Now let's look at this next one. So t squared should turn into something like 2 factorial over s to the 3rd power, but we need to do some shifting here by this minus 3. That'll give us 2 factorial, which is 2 over s plus 3 to the 3rd power. Again, because of the shifting. Okay, let's look at this next one. We want to take the inverse Laplace transform of 1 over s minus 1 to the 4th power. So we want to go in that direction. So this thing is missing the factorial that we have right here. Now you can eyeball it and see which constant you need, but maybe since this is our first one, let's not do that. So this is going to be the same thing as 1 over 6, because that's 1 over 3 factorial. And then we'll have the inverse Laplace transform of 3 factorial over s minus 1. And I'm going to write this as 3 plus 1 just so that we see the structure. We've got n factorial s to the n plus 1. So this will leave us with something like this. We have 1 over 6, and then we'll have t cubed. That's because we have this 3 factorial and this 3 plus 1, but then we have some shifting, so we need an e to the t because we've shifted by 1 unit. Okay, nice. Now let's look at this one. We've got the inverse Laplace transform of 1 over s squared minus s plus 2. Well, in order to do something like this, in fact, what we need to do is to use partial fraction decomposition. So let's take 1 over s minus s plus 2, and note that it's the same thing as 1 over s plus 2 times s minus 1. Something like that. Now, I mean, we're deep into this differential equations class, so likely you know how to deal with partial fraction decomposition. So I'll just write out that this turns into 1/3, and then we'll have 1 over s plus 2 minus 1 over s minus 1. So that's the partial fractions decomposition for that rational function. But then, like I said before, the Laplace transform is a linear transformation, so we can bring this 1/3 out, and then we can also factor this inverse Laplace transform across these two summands. So we'll have the inverse Laplace transform of s plus 2 minus the inverse Laplace transform of 1 over s minus 1. Okay, great. And now let's apply the inverse Laplace transform to each one. So we'll have 1/3, and then this will give us e to the minus 2t minus e to the minus t. Again, looking at this line right here in reverse. Or maybe by looking at that previous example that we did. Okay, so that's good. We've got a couple of examples of Laplace transforms and inverse Laplace transforms for polynomial functions and also for exponential functions. Well, now let's explore what happens with trigonometric functions. Next up, we want to calculate the Laplace transform of cosine b of t and the Laplace transform of sine b of t, which we'll denote by capital F of s and capital G of s. And here we're going to use a nice trick that calculates both of these Laplace transforms at the same time. Okay, so let's start with F of s. So we've got F of s is, like I said, the Laplace transform of the cosine of bt, but applying the definition of the Laplace transform, that'll give us the integral from 0 up to infinity of e to the minus st times the cosine of bt dt. Great. We have the product of a trigonometric function and an exponential function, or in other words, the product of two transcendental functions, which points us to using integration by parts. So let's use integration by parts here. Perhaps we'll choose our u to be equal to e to the minus st. So that tells us du is equal to minus s e to the minus st dt. And then we'll take dv to be equal to cosine of bt dt. That means v, by taking the antiderivative, is 1 over b times the sine of bt. Okay, so now let's put those into our integration by parts formula. Let's recall that that will be equal to u times v. So that gives us e to the minus st over b times the sine of bt. We need to evaluate that from t equals 0 to t equals infinity. And then we'll have minus the integral of v du. Notice the minus sign will cancel here because we've got a minus built into du. That'll leave us with something like this. Plus s over b, we can factor both of those out because they're constants with respect to the t integral. And then we'll have the integral from 0 to infinity of everything left over, which is e to the minus st times the sine of bt dt. Great. So now let's note as t approaches infinity, sine just bounces between +1 and -1, and this exponential decay function will just zero out. But then when we evaluate this at t equals 0, we know that sine of 0 is 0. So that means this whole thing turns into 0. Okay, that's good. And now let's look closely at what we have left over. We have the integral from 0 to infinity, e to the minus st times sine of bt, but that's exactly the Laplace transform of sine of bt, which we've called g of s. So maybe summarizing this, we have f of s is s over b times g of s. So let's write that down here. We have f of s is s over b times g of s. So we've got this nice equation that relates our Laplace transform of our cosine function and the Laplace transform of our sine function. Now let's see if we can get a similar equation if we do integration by parts starting with g. So let's start with g of s. So writing that out, that'll be the integral from 0 up to infinity of e to the minus st, and then we'll have the sine of bt dt. But this is also an integral of a trigonometric function and an exponential function, which points us towards doing integration by parts again. So let's do that. We'll make the same sort of choice. Let's choose u to be equal to e to the minus st. That tells us that du is the derivative minus s e to the minus st dt. Then we'll have dv will be the trigonometric part. That is the sine of bt in this case, dt. And that means that v is equal to minus 1 over b times the cosine of bt dt by taking the antiderivative. Okay, so now writing this out, we'll end up with something slightly different this time. We'll have u times v, so that'll be minus e to the minus st over b times cosine of bt, evaluated from 0 to infinity. And then we'll have minus the integral of v du. But let's see, we've got 3 minus signs all together, one from here, and then one built into the integration by parts formula. We can bring this s over b out, so this is going to be minus s over b. And then we'll be left with the integral of e to the minus st times cosine, but that's exactly f of s. So I'll go ahead and write that as f of s. Now let's see what happens with the evaluation of this function. So letting t tend towards infinity, the cosine function again bounces between -1 and +1. The exponential function will go to 0 because we have exponential decay. Then evaluating this at 0, well, the cosine of 0 is 1 and e to the 0 is also 1. That's in the lower bound though, so that's going to change this minus to a plus, which means we can summarize this as g of s equals 1 over b minus s over b times f of s. So let's maybe put a purple box around that. Okay, now let's bring those two facts to the top, and then we'll solve these equations for f and g. So based off the fact that f of s was the Laplace transform of cosine and g of s was the Laplace transform of sine, we just derived the following two formulas or equations that relate capital F and capital G. And so now let's smash them together to solve for f and g. Maybe the easiest thing to do looking at it would be to replace this appearance of f of s with s over b times g of s. So let's see what that'll leave us with. So we'll have g of s was 1 over b minus s over b. And like I said, we're going to replace that appearance of f of s with this guy right here. So that'll be s over b times g of s. Now we could maybe put some stuff together. That'll leave us with 1 over b minus s squared over b squared times g of s. Then we could add that s squared over b squared g of s to the other side of the equation, leaving us with 1 plus s squared over b squared times g of s. When we group the g of s terms and factor, equals 1 over b. Okay, so now this is looking pretty good. Maybe the next thing that I would do is find a common denominator for this. Let's replace 1 with b squared over b squared. And that means this numerator becomes b squared plus s squared over b squared. Next up, we can maybe cancel this 1 over b down to just the number 1 if we cancel out this exponent right here. And now we have b squared plus s squared over b times g is equal to 1, which means that we could multiply by the reciprocal of this and end up with g of s equals b over s squared plus b squared. And I've changed the order there, but this is maybe the more standard or traditional way to write this down. And now that we have this, it's super easy to calculate f of s. We can take this expression for g of s, throw it into this first equation that I have right here, and we'll end up with f of s equals s over s squared plus b squared. That's because this b in the denominator cancels this b in the numerator, and then we end up with a new s in the numerator. Okay, so there's our f of s, which is the Laplace transform of cosine, and our g of s, which is the Laplace transform of sine. So let's go ahead and add those to our chart over here and do some examples. So let's look at two examples of Laplace transforms, and then we'll do an example of an inverse Laplace transform. So let's start with the Laplace transform of e to the 2t times sine of 3t. So the fact that we have a sine of 3t here means we should follow this format here. So the role of b is being played by 3. That'll give us a 3, and then we'll have something squared plus 3 squared, which is 9. Now, if there was no exponential here, that would merely be s squared. But since there's an exponential function here, we get the exponential shifting rule where we replace every s with s minus 2 in this case. So that means here we have an s minus 2. So that's what we get if we put all of these rules that we've developed together. Now we could simplify this if we wanted to, And that would be maybe a good idea because generally you'll see problems in this simplified version and have to take the inverse Laplace transform. Okay, so we'll have 3 over s squared minus 4s plus 13 when all is said and done. Okay, let's look at this next one. We've got the Laplace transform of cosine squared. Well, cosine squared is not on our chart, but if you remember carefully, there's a power reducing formula for cosine. And in fact, we can write cosine squared as 1/2 and then 1 plus cosine of 2t. Great. Now we can use the fact that the Laplace transform is a linear transformation. That'll give us a half. We'll have the Laplace transform of 1, which is merely 1 over s from our very first example. It's also of this type right here where t is equal to 0. Then we'll have the Laplace transform of cosine of 2t. So that'll give us s over s squared plus 2 squared, which is 4. And there we've got our Laplace transform of cosine squared. Okay, so now let's do a big example where we calculate an inverse Laplace transform. Okay, so let's look at the following example. Our goal is to find the inverse Laplace transform of 3s plus 8 over s squared plus 2s plus 5. I'll just maybe tell you that s squared plus 2s plus 5 does not factor. You can check that by looking at the discriminant though. So that means that it's an irreducible quadratic. But if it's an irreducible quadratic, then via completing the square, we can make it look a little bit like one of these, hopefully. So let's do that. Notice that if we have s squared plus 2s plus 1, then that will definitely factor. So let's maybe put that as a little note. We'll put it down here so we have enough room. So we've got s squared plus 2s plus 5 is the same thing as s squared plus 2s plus 1 plus 4. But that's the same thing as s plus 1 squared plus 4. Okay, so that's looking good. So now let's rewrite this as the inverse Laplace transform of something over s plus 1 squared plus 4. Okay, so that motivates me that I should have something which is like a cosine 2t times e to the t, just given the shifting here. Or perhaps a sine 2t times e to the t. Okay, now what can we do with this 3s plus 8? Well, we'd like to write the s part so that it has an s minus 1 built in to match what's going on here together with the shifting. So let's do that. We could write this as 3 times s plus 1 plus 5. I think that would be a nice way to do it. Notice if we were to expand that out, we would most definitely get 3s plus 8. Now we're essentially ready to finish this thing off. Let's just be careful with everything. So we'll have 3 times the inverse Laplace transform of s plus 1 over s plus 1 squared plus 4. That is the first term. And then we'll have plus, I'm going to take a half out of this and write this as 5 over 2, just we'll see why. And then we'll have the inverse Laplace transform of 2 over s plus 1 squared plus 4, viewing 2 as the square root of 4 or 4 as 2 squared. And I took that 2 out so that I would have this matching number right here. And now we're ready to do it. So notice this is going to be 3 e to the t, and then that's either sine or cosine. Let's see, it's got the variable on top, so that means it's cosine. So this is going to be cosine of 2t. And then here will be 5 halves e to the t, and then we'll have the sine of 2t. There we do not have the variable up top, so it's the sine function. Okay, and that would be our inverse Laplace transform. Okay, let's do one more example. Now for the last example, and albeit I did skip a step here, but that's because this step is something that you've done in a previous class. In fact, if you're in my class, then likely for most of your homework, all but maybe one problem, you could use Mathematica to do this step for you. Okay, so we want the inverse Laplace transform of 3s plus 2 over s squared plus 1 times s plus 1 times s plus 2. So anytime you've got a rational function like this, what we want to do is decompose it using partial fraction decomposition. So notice we have two linear terms here, s plus 1 and s plus 2. So I've got a over s plus 2 plus b over s plus 1. And then we've got this irreducible quadratic s squared plus 1. Then that's going to exhibit over here as my cs plus d over s squared plus 1. Like I said, I worked out the details here, and what you end up with is 4/5 1 over s plus 2 minus half 1 over s plus 1 minus 3/10 s over s squared plus 1 and plus 11/10 1 over s squared plus 1. And I wrote it like that because now we can apply these rules over here. So notice we'll have 4/5 and then we'll have e to the minus 2t by this shifting rule right here where we just have the function g as the constant function 1. And then we'll have minus 1/2 e to the minus t for the same sort of reason there for that second linear term. And then we'll have minus 3 over 10. So we've got s over s squared plus 1, that will be cosine of t. And then plus 11 over 10, and that will be sine of t. And that's our inverse Laplace transform. Okay, so now I'm going to leave you with a couple of warm-up exercises. So I'll leave you with 4 warm-up problems, and these can all be solved using this basic chart that we had right here. So 2 of them are to find the Laplace transform. This first of the function cosine of 2t plus e to the minus 3t sine of 5t, and this second one of the function t to the 4th minus 3t squared e to the 6t. And then the inverse Laplace transform of s over s squared plus 2s plus 1. And then finally the inverse Laplace transform of 1 over s minus 2s plus 6 over s squared plus 4. And that's a good place to stop.